Right, hi Year 11s. This is a video on chemical bonding relating to the covalent bonds. It's a kind of add-on. It's about coordinate covalent bonds, polyatomic ions, and non-octet rule elements. So let's get started. All right, so this is what we're going to learn about. Okay, so we're going to start with coordinate covalent bonds. So what are these? Let's have a look. Covalent bonds, so these are the normal ones that we've learned about, are the bonds between shared electrons, we do that, generally with equal contribution from each atom within the bond. Okay, so effectively, if you've got a double bond, 2 electrons come from one atom and another 2 electrons come from another. Or if you've got a single bond, you've got 1 electron coming from one atom and 1 electron coming from another. Right. However, coordinate covalent bonds are between shared electrons, so that's still the same. All right. But the contribution of those electrons comes from only one atom within the bond. Okay, so instead of it being a single bond where one electron comes from one atom and another electron comes from another, both of the electrons will come from one of the atoms rather than 2 of them. All right, so some examples of these, right, are the acids, of the polyatomic acids. All right, carbon monoxide and ozone. We're going to start with the ozone first. So ozone is O3, right? It's an oxygen molecule. Here we go. But another oxygen tags along, and what it does is that it uses these 2 electrons. So those 2 electrons are the shared electrons, but they're coming from only one atom. They're coming from this oxygen here. So these 2 here are shared, but they're only from one atom. So this oxygen here is effectively using those 2 electrons to complete its outer shell. All right, and then if you were to draw this with lines, you would draw this with O double bonded there and a single bonded there, and then you would have the non-bonding electrons shown as well. Okay, 2 there and some there. Okay, so that is ozone. Ozone. Let's have a look. Let's go look at the next one, carbon monoxide. Okay, so you've got the carbon, you've got the oxygen, right? 2 electrons come from this carbon here. It's only got 4. It double bonds to this oxygen, but this oxygen having 6 electrons, 2 of them are actually within the double bond. Okay, so it doesn't only come from only one atom, but it's an uneven balance. It's not equally shared. All right, so these 1, 2, 3, 4, 5, 6 electrons are the bond, are the shared electrons, but 4 of them come from the oxygen and 2 of them come from the carbon. All right, and so to draw this, you would, with lines, you would draw 1, 2, 3, all right, and you would draw this with an arrow to show the coordinate covalent nature of it. All right, then you'd be able to show 2 of them here and 2 of them there. Okay, right, that's that one there. Let's go have a look at another one. Let's do H2SO4. All right, H2SO4. Let's have some more room. Right, so we start off with an S in the middle. Okay, so whenever you draw these acids and their derivative ions, you start off with the central atom. These will have a OH structure like this, okay, coming out of the central atom, right? And that's one of them. Here is another one. And now you have accounted for the S and the 2 H's. Okay, this sulfur has 6 electrons. Okay, so that sulfur automatically has 1, 2, 3, 4, 5, 6 electrons. Right, so effectively sulfur has its full set of 8 electrons to make a stable electron shell. Right, however, the oxygens do not, so they tag along here. And they use the electrons, these ones here, which were non-bonding, and now they're being used for the oxygens here to make their complete outer shell. Right. H2SO3 is exactly the same structure, except it doesn't have the oxygens here. Okay, so it doesn't have one of those oxygens there, and that's H2SO3. Okay, Let's do HNO3. Okay, nitrogen in the middle, a single bond to an oxygen, single bonded to a hydrogen here to account for the hydrogen. The nitrogen has 5 electrons, so 1, 2, 3, 4, 5. And so now it's got a double bond with one of the oxygens to make a stable 8. So now the nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it's stable. Okay, but it's going to have an oxygen use 2 of those non-bonding electrons for its own bonding, okay, for its own stable electron configuration. Okay, and then finally H3PO4. Let's do this one. Okay, so you've got a phosphorus in the middle. You've got 1, 2, 3, 4, 5 electrons around the phosphorus. Okay, it's going to bond, single bond with one oxygen here, single bond with another oxygen here, single bond with another oxygen here. So now the phosphorus has its full 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 with 3 single bonds. However, another oxygen will tag along and use the non-bonding electrons there to complete its stable electron shell. All right, so let's move on. Okay. Right, I think that we did all of those. Yeah. Okay. Oops. Okay, so non-octet rule elements. So non-octet rule elements are elements that don't need 8 electrons to complete their valence shell. Okay, so these ones are a bit weird, right? But you have Be, which is beryllium, which you might think is a metal, but it has also the ability to covalent bond. Okay, and it will covalent bond with this fluorine or some fluorine in this particular manner. Okay, and if you look, it only has 4 valence electrons and its shell is full, or its shell is stable enough to make that molecule. All right, so that's beryllium. It can have a 4 electrons in its outer shell. Okay, boron can have 6, so boron has 3 originally. It's going to single bond with these fluorines to make it 6. Okay, so it has 1, 2, 3, 4, 5, 6, and that's stable there, so that's boron trifluoride. Okay, nitrogen monoxide and nitrogen dioxide. Let's have a look. So nitrogen monoxide, okay, 1, 2, 3, 4, 5. Well, actually, no. 1, 2, 3, 4, 5 on the nitrogen, 2 on the 6 on the oxygen. We have a double bond here where you've got 4 of those electrons being shared for the nitrogen and the oxygen. The oxygen is 8, that's perfectly fine, but the nitrogen only has 7. Okay, and so that's how nitrogen monoxide forms, or is. Then we have nitrogen dioxide. Nitrogen dioxide will form again a double bond with the oxygen. It has these 2 here, so this is nitrogen monoxide, and then another oxygen can come here and sit on those 2 electrons and use those up. All right, you can see that this then is also coordinate covalent bonding of those 2 electrons, as well as a non-octet of the nitrogen here, because it's only got 1, 2, 3, 4, 5, 6, 7. Okay, so nitrogen dioxide. Okay, phosphorus pentafluoride. Okay, so let's do that. Phosphorus pentafluoride, 1, 2, 3, 4, 5. Okay, and you would make a single bond with each of those fluorines, and each of those fluorines is going to have 6 on the outside. Okay, and then you'll see that there are 10 electrons being shared with the phosphorus. Right, when you do these, you have to draw them in a nice pretty star shape. Okay, so that you can fit them all in. All right, so that's phosphorus with 10, and sulfur, not with 10 as well, but only with 12. So sulfur can form 12, okay, because it's got 1, 2, 3, 4, 5, 6 electrons. They're all going to single bond to an F. And so you're going to end up with sulfur hexafluoride. 6. Yeah, you get the idea. So that's sulfur hexafluoride. Those are the non-octet rule elements. Okay, so they exist there. The fluorines can often be converted to chlorines as well. They'll also form similar things, so like PCl5 or something like that. All right, so polyatomic ions are ions that comprise of multiple atoms. Okay, and we kind of might have dealt with this already in ionic bonding, but acids form polyatomic ions when they lose a hydrogen from their molecule. So that's the sulfate, nitrates, carbonates, phosphates, and sulfite ions. But the hydronium and ammonium and the nitrite ions are also things that we kind of should know as polyatomic ions. Again, you should memorize all of your ions, but this is how we draw some of those out. So the sulfate ion, let's go back to this here over here. All right, I'm going to grab this. Nope, that didn't work. Right. I'm going to grab this. Okay. And then I'm going to move it around. I can move it over here. And continue to move it over here. Okay, so ignoring that crossed out sulfur, right? What will happen is that you will lose a hydrogen, okay? And then you'll form a 1- ion. So that's HSO4 minus. Then when you lose the second one, right, you'll form SO4 2 minus, because there's only going to be the S and the 4 oxygens. Okay, so effectively what that might look like if I was to finish drawing that properly. Okay, 1, 2, 3. This is the coordinate covalent bond oxygen. This is an oxygen which has an extra electron that did come from the hydrogen, but the hydrogen is no longer there. Same on this side. And then this one here is another coordinate covalent bond. Okay, and then you would draw that with square brackets because it's an ion and with a 2 minus there. Okay, and that's the same with all of the acids. You just take off the hydrogens and then you you draw it, and then you just don't draw the hydrogens at the end or remove them, and then you can add the square brackets and then add the charges in. Let's go through these other ones. The hydronium ion is H3O plus. Okay, why is that so thick? I don't know. Okay, so H3O plus is a hydrogen. Well, it's a water, so H2O. But it's got an extra hydrogen on it, which is using those 2 electrons as a coordinate covalent bond, and you need to give it a charge of +1. So this is a polyatomic ion which has coordinate covalent bonding as well. All right, so hydronium, ammonium is next. Ammonium is NH4 plus, and so if it starts off with like an ammonia, which is NH3. So this is NH3 with a lone pair there. Again, a hydrogen comes here, right, and uses these 2 electrons here, right, and you end up with a NH4 plus ion there. Okay, so coordinate covalent bond here as well. So for the last one, it's nitrite, which is no, it's not, NO2 minus. I'm going to let you have a go drawing that yourself. Think about what it would look like as an acid, as HNO2, and then remove the hydrogen and then work out what it will look like. Right, and then here it is as the structure. You should see that, there is a double bond here to 1, a single bond here to the oxygen. The hydrogen would be here, and that'd be the electron that came from the hydrogen, but it's been removed, and so therefore this hydrogen's fallen off. Right, and you put the square brackets in and you put the charge in there as well. All right, so that's it for this particular video. Adios.